Hello. In our last lesson, we went over how to solve single variable absolute value equations. So in this lesson, we want to move on and learn how to solve single variable absolute value inequalities. So how we're going to do this is we're going to take what we just learned about solving single variable absolute value equations, and then we're going to take what we already know about solving inequalities, which we've been doing for several weeks now, and we're going to combine them. And that will enlighten us on how to solve inequalities that involve absolute value terms. So let's start with a pretty simple example. We'll do absolute value of n plus 4 is less than 13. So our first step, just like when we were solving equations, is that we want to isolate the absolute value term. So in order to do this, we're going to want to subtract 4 from each side, and we'll get absolute value of n is less than 9. So when we're at this point, again, just like we're solving an equation, we're going to split it into two separate inequalities. And we call this a compound inequality. So the reason that we take absolute value inequalities and split them into two different inequalities is because we have to account for the case where what's inside the absolute value sign is positive, as well as the case where what's inside the absolute value sign is negative. So the positive case, just like equations, will just be n is less than 9. The negative case, just like absolute value equations, will be negative n is less than 9. So this side is already solved for us. We have n is less than negative 9. On this side, we distribute the negative to the inside. We only have to distribute it to one term here. We get negative n is less than 9. And then, if we multiply or divide each side by negative 1, we'll get n on this side. We'll get negative 9 on this side. And remember, in an inequality, if we multiply or divide each side by a negative number, we need to flip the sign. So we get n is greater than negative 9. So let's graph this on a number line. So we'll have our number line here. We'll have 0. We'll have 5. We'll have 10. We'll have negative 5 here. We'll have negative 10 here. And we're going to want to graph both of these on the number line. So you have n is less than 9. So we can plot 9 right over here, and we'll shade like that. So that would be n is less than 9. On the other component of the equation, we have n is greater than negative 9. So we're going to plot negative 9 here, and we're going to shade in this area here. And the answer to our problem is going to be the area that's shaded by both. So I did make one mistake here. We have n is greater than and n is less than, so these should be an open circle. Open circles here. And our answer on a graph is going to look like this. It's the area that's shaded by both of our inequalities. So thus what we can do is we can use the language either n is less than 9, or n is greater than and n is greater than negative 9, we use the language and because the inequality has to satisfy both of these components of the compound inequality, or we can combine these two inequalities and write it as negative 9 is less than n is less than 9. So again, we could either write it this way, or we could write n is less than 9 and n is greater than negative 9. And what this and tells us is just that our answer must satisfy both of these inequalities. So it's not an either or. It's not. So for example, if n is equal to 11, it will satisfy this inequality, but it won't satisfy this one. So n is equal to 11 is not a solution. Whereas on the other hand, n is equal to 1 does satisfy both of these inequalities. So n is equal to 1 is a solution. So we just did a case where we had less than. So now let's go to a situation where we have greater than. Let's say we have the absolute value of 2x minus 3 is greater than or equal to 11. So in this example, our absolute value term is already isolated. So we can get right to the splitting. So in one case, we have the positive case, 2x minus 3 is greater than or equal to 11. In our other case, we would have negative 2x minus 3 is greater than or equal to 11. So in this case, we're going to want to add 3 to each side. We're going to get 2x is greater than 14. And then if we divide by 2, we would get x is greater than or equal to 7. So let's draw our good friend the number line again. I guess since we don't know exactly what the range of this problem is going to look like, let's plot a 7 over here. And we have x is greater than or equal to 7. So since it's greater than or equal, I'm going to draw a solid dot. And I'm just going to shade in that area. So in our next case, we distribute the negative. We get negative 2x plus 3 is greater than or equal to 11. We subtract 3 from each side. We get negative 2x is greater than or equal to 8. Then we divide each side by negative 2. We're dividing by a negative, so we have to switch the sign. And we would get x is less than or equal to negative 4. So let's plot negative 4 on our number line over here. And I'm going to shade in this side. So we'll notice something interesting here, which is that our answers do not overlap at all. So what does this tell us? What this tells us is that when we start out with the absolute value term is greater than something, we have a different case. And in that case, we would have x is greater than 7 or x is less than or equal to -4. So the reason we have this is because if we have a really big term for x, which would be encapsulated by this x is greater than 7 part, the absolute value is going to be greater than 11 because we're just going to have a big positive number over here. So let's look at an example. Let's look at, like, say 10. If we look at the case where x is equal to 10, we'd get 2 times 10 minus 3 is greater than or equal to 11. We get the absolute value of 17 is greater than 11. So we know that that's true. Additionally, if we take a negative number and take a big negative number, we're going to get the inside of the term is going to be a bigger negative number, or in our case, a smaller overall number. And if we take the absolute value of that big negative number, it's going to make it a big positive number, and it'll be greater than or equal to 11. So let's look at the case of, say, -20. We would get the absolute value of 2 times -20 minus 3 is greater than or equal to 11. And we'd get the absolute value of -40 minus 3 is greater than or equal to 11. We get the absolute value of -43 is greater than or equal to 11. And then, if we apply the absolute value sign, we just get 43 is greater than or equal to 11, which is true. So both of these are true. It makes us happy. And our final answer to this inequality is x is greater than or equal to 7, or x is less than or equal to -4. So again, it's a little bit tricky, because if we have a greater than symbol, we have an or situation, which looks like this. And if it's x is less than or equal to something, we get an and situation where we have those overlapping inequalities. So in our next lesson, we'll do a couple more examples like this that will hopefully help to reinforce these concepts.